Hello, good evening, everyone. Here we are again with Mr. Chu. We are going to continue from where we stopped yesterday. Yesterday, we stopped at the objective section for the chapter 3, which is chemical bonding. So today, we are going to continue with the section B of these structured questions for chemical bonding. So if you like my video, please help me to click like. And if you want to receive further notifications, do subscribe and hit the notification buttons on your right. Okay, so without hesitation, let's begin our lesson. So I hope that you already have the modules with you and you are ready with the questions. So if you are ready with the questions, let's together learn on how to answer the STPM semester 1 chapter 3 for section B questions. So I'll be showing you tips on how to answer correctly, and you should be able to understand, better at the end of the lessons, okay? So let's start with question number 1. Phosphorus trichloride PCl3 was used herbicide and insecticide in 1970s. Due to its toxicity, it's not frequently used nowadays. 1. Draw the Lewis structure of the phosphorus trichloride. So you're expected to use the 4 steps of this covalent compound. Now, if you are not sure on how to use the 4 steps on how to deduce the Lewis structure, so I'm going to illustrate for you, so hopefully that you'll be able to understand better. So here are the 4 steps. If you refer to the module, it will show you clearly on how to propose the 4 steps. Starting from step 1, you calculate the total valence electron. So phosphorus is from group 15. So it's group 15, that means you have 5 valence electron. And then chlorine is from group 17. So you should have 7 valence electron, and because you have 3 chlorine, so you have to multiply by 3. So this will make the total electron is equals to 26. Okay, our second step will be place a chemical bond between the surrounding atoms to the center atom. So there you have 3 chlorine. Now in here, usually the one with the smallest number of the atoms will be the center atom. Like in this case, PCl3. So P will be the center atom. So now you build up 3 bonds. So 3 bonds use 2 electrons. Okay, so total electron used up is 6. Okay, so what about the remaining electron? So the remaining electron will be 20. Okay, so then the third step will be placing the surrounding electron with octet configuration. So for each atom, all you need to do is just place 6 more electrons toward it. Okay, so I'm going to show you on how to place the 6 electrons around it. Okay, so this is how you place. Okay, so if you look carefully, 1 atom is equals to 6 surrounding electron to make it to become octet. So 3 atoms multiplied by 6 electrons, so you get 18 electrons. So the remaining electron will be 2. So if you have now remaining electron 2, so where should you put? It will be at the last step, 4th step, you put at the center. So this is how basically a PCl3 looks like. Okay, so do we really need to necessarily draw the as per shapes of the molecule? Actually no need. Even if you draw in a triangle shapes or whatsoever shape, it is okay, because we are now drawing Lewis structure. As long as you must have the surrounding electrons to be correct with the octet configuration, shouldn't be much of a problem. So that is how you score 1 mark for number A1. Number A2, name the hybrid orbital of phosphorus in phosphorus trichloride. So the hybrid orbital is between 3s and 3p. So the hybrid orbital in here is sp3. Okay, because it is surrounded by 1 lone pair electron, okay, and 3 surround atom. Okay, so lone pair electron is assumed like the surrounding atoms too in the hybridization theory. So that is why you have sp3 in here. Okay, hence name the shape of the phosphorus trichloride. So this is obviously a trigonal pyramidal. So this is how we answer number 1A. Immediately we go to 1B. When heated with excess chlorine, phosphorus trichloride can eventually form phosphorus pentachloride PCl5. Write a chemical equation for the formation of phosphorus pentachloride from a phosphorus trichloride. So you write the equation PCl3 plus Cl2 give PCl5. Do you need to write the state of matter? So up until here, so far, we're not yet really stressed on the state of matter. So even if you don't really write the state of matter, it is okay. But the most important part in writing a chemical equation we are asking for is balancing. Okay, so this one is pretty obvious that this is how you balance the electron. Then we goes to number 2, write the valence electron of phosphorus in phosphorus pentachloride. So in here, you need to understand the type of hybridization undergoes by PCl5 first. So the type of hybridization, now this is slightly a little bit out of syllabus from STPM because the hybridization take place in here is actually what we call as an sp3d, okay? sp3d1 to be more specific. Okay, so we just usually we don't say 1, we just say D. Okay, so this is the hybridization. So the hybridization will reflect how should the valence electrons of the phosphorus be, because it is made of 1 3s, 3 3p, and then 1 3d orbitals in here. So based on the electronic configurations in here, so you can see clearly that the electronic configurations of the phosphorus in phosphorus pentachloride is 3s1, 3p3, and 3d1. Then number 3, explain why nitrogen, which is the same group as phosphorus, can only form nitrogen trichloride but not nitrogen pentachloride. This one you have to understand. In here, if you look carefully, PCl5 will have 10 surrounding electron. So if phosphorus pentachloride has 10 surrounding electron, then you should know by yourself that why nitrogen cannot, because nitrogen is from second period. So when you have a second period, you will only have s orbital and p orbital. That will make the total number of electrons available for the second period elements to be 8 electrons only. Hence, they cannot have more than 8 electrons. Okay, so you should answer S, since nitrogen is from period 2, or you say it have 2 shells, so it does not have MTD orbitals available for it to fill in the electrons. Okay, so that is how you answer for question number 1. Now, immediately we go to question number 2. Carbon is one of the most important and essential elements in all living things. Number 1. A, using arrow to represent electrons, show the energy level diagram of the electronic configuration in ground state and excited state. So in ground state, the carbon is written as 2s2 and 2p2. So this is according to Aufbau principle and also Hans principle, where in the 2p you are placing with a single electrons in here. However, when during hybridization, when it is undergoing excitation state, electron from the lower energy level somehow jump to higher energy level. Okay, so this will make the excited state for the carbon to be looks like this, 2s and 2p. Now at this moment, energy levels between 2s and 2p are to stay equal, so you must be able to present your energy levels to be equals in excited state, whereas in ground state it follows the Aufbau principle, so 2s is lower than 2p. So usually if this is a 4 marks question, 1 mark will go to the energy level sketching, and 1 mark will go to how you fill in the electrons inside the orbitals. So 2 times 2, that is given 4. So that is how you answer for number 2A. As for 2B, carbon atom use hybridized orbital to form a bond propene molecule C3H6. So state the type of hybrid orbitals involved. So in C3H6, if you are not sure, let's together draw the Lewis structure of the C3H6 first. Only then you'll be able to figure out what are the hybridization take place inside C3H6. So this is how C3H6 generally looks like. So it shouldn't be, even though you've not yet learned organic chemistry, but this is already something learned during your SPM level. So it shouldn't be an excuse saying that you don't know. So you should be able to sketch this one. So from the Lewis structure, you can clearly see that this carbon is surrounded by 4 atoms. Okay, all are bonding pair electron. So this one is obviously an sp3. While this carbon is surrounded by a double bond and single bond, this is obviously an sp2. So same goes to this carbon, which is also an sp2. So this will make the type of hybrid orbitals available in propene is sp2 and sp3 hybridization. And hence draw a label diagram indicating the overlapping of orbitals in the propene molecule, showing the type of bonds present. So you should be able to sketch the overlapping orbitals between the propene, okay, and labels accordingly which one is a sigma bond, which one is a pi bond, okay. So label diagram, of course, they need you to label the sigma bond and also pi bond, okay. So with that, that is how you generally answer question number 2, okay. So hope that you'll be able to do this one. By the way, don't worry about how your diagram looks like. The most important thing is, number 1, you should show how does the overlapping occur, and then label the sigma bond and also pi bond. So that should be enough. Do you need to exactly follow the shape that I draw inside the diagram right now here? Actually, no need, because this one is using computer, so it's convenient for me to draw. Okay, so this is how you answer for question number 2. Then immediately we go to question number 3. Draw the Lewis structure and state the geometrical state of SF6 molecule and I3- molecule for marks. So in here, Definitely, when it is 4 marks, you must know by yourself Lewis structure 1 mark and geometry 1 mark. Okay, so times 2, so that makes the 4 marks in here. So sulfur hexafluoride, if you use the 4-step technique that I showed you just now, so it shouldn't be much of a problem. So S is from group 16. F is from group 17 times 6. So times 6 fluorine. So there you have all total electron in here will be equals to 48. So 48 electron, all you have to do is just place sulfur and 6 fluorine, and generally this is how your molecular structure will look like for SF6. And then as for I3 minus, also the same. So you just use 17 times 7, because it's from group 17. So it's 7 valence electron times 3 plus 1. Why plus 1? Because it is the electron accept. Okay. So you have to also consider for the electron accept in here. Okay, so that is what makes it 22. Surround bond electron 2, surround electron 2. So this will make the iodine. We have 3 lone pair electron and also 2 bond pair electron. So this will give the iodine a linear shape. Okay, so very, very straightforward and direct question. Frequently asked in STPM, including iodide ion. So you should be able to draw them and name their shape accordingly. Okay. Okay, B, state why SF6 is used as insulating gas in electrical appliances. So in here, you can see that sulfur fluoride in here is a covalent compound. So when there is a covalent compound, why is it suitable as an insulating? Insulating means that cannot conduct electricity. So this is because it is a covalently bonded molecule, and the gaps between the conduction band and valence band is very large. Sometimes you might also want to try your luck saying that it is a covalent compound with no free moving electron also can. Okay, so you can also answer that, no problem. Okay, then number 2, Si6 does not exist. So can you imagine how Si6 generally looks like? Because sulfur is from period 3, okay, and iodine is from period 5. So iodine is so much more bigger than expected compared to the sulfur. So can you imagine when this sulfur is surrounded by 6 very bulky iodine in here? How would it imagine? So in here, the iodine can no longer fit inside the space already. So such effect is also known as what we so-called a steric hindrance. Okay. Or you can also describe what is a steric hindrance. Steric hindrance is an effect where a molecule becomes unstable because of the bulky surrounding molecules bonded to the center atom. So that is why it cannot be formed. Okay. So this is for number 2. Number 3. I3 minus can exist under standard condition, but F3 minus cannot. 2 marks in here. So can you imagine if now I changes the I to become F? Okay, do you see that? And in here, fluorine is to say among the smallest atom in group 17. So can you imagine what will happen now is fluorine with such a small atomic size, okay, it contains a lot of lone pair electron, and we learned from the VSEPR theory stating that lone pair electron repulsion is the greatest, followed by lone pair bond pair, and then finally bond pair electron. So too many lone pair electrons surrounding in a small fluorine atom will make the fluorine atom to become less stable. So as a result, fluorine, because of the repulsion of stronger repulsion between lone pair electron, therefore cannot form. And furthermore, fluorine is from period 2. Isn't it? So if period 2, the maximum number of the electrons that can be occupied by fluorine is only 8. Now look at the fluorine in here. Fluorine now has 10 electrons. So can it exist? It cannot. So for safetyness, you might want to write both of the factors together, because here is 2 marks. So that means you have to write 2 factors inside here. So F does not have empty d orbital. So as you said, cannot expand its octet also can. Okay, and finally, you must just say that stronger repulsion by the lone pair electrons inside the fluorines. Okay, so that is how you are also you are going to answer for question number 3. So immediately we move to question number 4. Sulfur tetrafluoride is a reactive, stable, and highly poisonous gas. Draw the Lewis structure of the sulfur tetrafluoride. Again, you use the same technique as the 4-step technique. Sulfur is from group 16, so you have 6 valence electron. 6 electron, and then fluorine is from group 7, so you have 4 So you multiply 17. So you have 4 sulfur. So 4 times 7 electron. Now you have a total electron is equals to 34 electron. Okay, then the second step will be you place the sulfur in between this one. Okay. So you should have 4. So you minus 2 times 4, which is 8. Okay. So you get 26. So 26, you make the surrounding to become octet first. Okay, you make the surrounding become octet first. So you have 4 times 6, which is 24. So you have remaining 2 electron left. So the 2 electron left placed at the center of the sulfur in here. Okay, so this will make SF6, SF4 looks like this. Okay, okay. So this is number 1. Then number 2, what is the shape of the sulfur tetrafluoride? So since in here you have 4 bond pair electron and 1 lone pair electron, so therefore the shape in here will be a seesaw shape. Okay. Then number 3, is sulfur tetrafluoride a polar or non-polar molecule? So due to the presence of the lone pair molecule, it will repulse the angle from the fluorine, making it to become non-symmetrical, hence a polar molecule. Okay, it is a polar, sorry, it is a polar molecule. I typed wrongly here. It is a polar molecule. Okay, it is a polar molecule. Okay, B actually. Cyanide ion Cn- can act as a monodentate ligand. Draw an overlap orbital diagram of the cyanide, state the hybridization. So in here, you draw the overlap orbital diagram for the cyanide and state the hybridization. So the hybridization takes place in sp, Cn is sp hybridization. Okay, so how are you going to draw the cyanide ion? So you have to imagine what happened in the carbon ground state, excited state. So you have, of course, first of all, you need to know how does the Lewis structure of the Cn- looks like. Cn- is C triple bond N, but the negative belongs to the carbon. If you learn formal charge, you eventually find out that the negative charge belongs to the carbon, not belongs to the nitrogen. Okay, so in here I shall not explain further what is formal charge. So if you want, you might want to find out on your own through internet, through Google. So still, if you cannot understand, then you let me know. You inbox me, then I will try my best to show you what is actually a formal charge in here. So now let's focus back on the question. As you can see in here, there are C triple bond N. So when there are C triple bond N, when you prepare the orbital, you must know by yourself that in C triple bond N, okay, so you must have what we so call as 1 sigma bond and then 2 pi bond in here. So 2 pi bonds means that you have to prepare 2 unhybrid orbitals to form the hybridization with the Cn and 1 direct overlap in between the Cn. So at the end of the day, this is how the Cn- looks like in here. Okay, so I will also advise you all to place the type of bond, including this is where I label inside that one. Okay, I also advise that this one you label as pi bond, you label as a sigma bond, and in here, and then you might also want to describe the angle, because this one is very hard to estimate where the marks located. So if I were you, I would definitely place all the bonding angles inside here, 180 degree, what is the shape, linear, etc. Okay, and the negative should be able to go to the carbons in here. Okay, so usually in STPM style, drawing the structure 1 mark, labeling 1 mark, and make sure that the negative belongs to the carbon is 1 mark. So altogether 4 marks in here. Okay. Okay, so that is how you answer for number 4. Immediately we go to question number 5. In urine, phosphorus element exists as a phosphate PO3-. So what is the shape of the PO4-3- looks like? So for information, this is how phosphate ion looks like. So generally, this is how phosphate ions looks like. Now, if you are going to ask me, how do we actually draw the Lewis structure of this one? I can only say that you have to memorize a little bit on this one. Because this phosphate ion structure, if you use the 4 steps technique that I shows to you, you won't be able to get this diagram. Okay, you will get P with 4 single bond, not this diagram. actually. So that's why I said in the four-step Lewis structure, yes, it can be generally applied to many other compounds, but there are certain anomalies that you cannot apply. For not only that you cannot apply the 4 steps inside PO4 3-, you also cannot apply the 4 steps inside SO4 2-, also cannot. Okay, you also cannot, if they ask you to draw ClO2-, O3-, okay, or O4-, okay, all of them also cannot be used the 4-step methods to draw the Lewis structure inside here, because they are a little bit different from the structure because of the formal charge problems too. Okay, so that is how. So in here we straight away goes to the question. So what is the shape of this ion? This is obviously a tetrahedral shape. Huh? Okay, number B, element X react with element Y to form compound Z. Electronegativity between atom X and atom Y are 1.0 and 3.5 respectively. 1, state the type of chemical bond in Z. So the type of chemical bond is actually ionic bond. So in here, how do we actually know when do you form ionic bond, when do you form covalent bond? There is these formulas that you can find also inside the module based on the difference of the electronegativity. Okay, it is to say that if the difference of electronegativity is greater than 1.8, so it is mostly ionic. Okay, and when you are lesser than 1.8, okay, it is mostly covalent. Okay, generally, this is just a general guideline, right? And it's between 0 to 0.4, then it is non-polar covalent compound. Okay, so this is the general guideline. For more information, you can refer to the notes inside the modules. Okay, so that is what I can show you in here. So very obviously, the difference between 1.0 and 3.5 is 2.5. So it is ionic bond. The Lewis symbol of the atom X and Y are shown below. So this is how X and Y looks like. So what is the chemical formula of Z? So looking at here, X is the second group, Y is group 16. So that's why you form a XY in here. Okay, so number 2, state two physical properties of Z. So because it is ionic compound, number 1 is definitely harder, stronger, high melting point, boiling point, soluble in water, good conductor in aqueous solution. You cannot just stop saying that good conductor, because this ionic compound can only be conducting electricity in 2 states. Number 1 is in the aqueous solution. When you dissolve ionic compound inside water, then it can conduct electricity. And then finally, is in the form of molten. So why is it that it's possible that it conduct electricity in both molten and also aqueous solution? Because in molten and aqueous solution, they have free moving electron or free moving ion respectively. So that is how they can conduct electricity. Okay, then we go for number 4. Decimal point of Z is stronger than that of Na2O. That means in terms of the strength of the ionic bond, it is to say that Z is stronger than Na. So state 2 factors. So what are the factors that influence the ionic bond strength in between the ionic compound? So generally, we say that the strength of the energy is directly proportional to the charge, yet inversely proportional to the ionic radius. Okay, so this is a general guideline. So in here, when you say, you can see from here, Z is from group 16, Y is from, sorry, X is from group 2, Y is from group 16. So you expected X to form 2 plus, okay? And then Y also form 2 minus in here. So they have a generally higher charge in here. And definitely the atoms for the ionic compound for the Z is definitely greater due to the, they are from the same group, and across the period when you have a higher effective nuclear charge. So that is why it is getting smaller, okay? Okay, so with that, that is how you answer essay question number 5. Immediately we go to essay question number 6. Table below shows boiling point and bond energy of the hydrogen halide. So this is boiling point and bond energy. So number 1, explain the trend of boiling point from hydrogen halide to hydrogen fluoride. Okay, you can see that hydrogen fluoride is exceptionally high. And then from HCl, HBr to HI, you can see in here, the boiling point eventually increased. So you must explain from both angles lah, stating that HF has hydrogen bond, while HCl, HBr, and HI are simple covalent molecule held by weak van der Waals forces. So what are the factors that will influence van der Waals forces? The primary factor that influence van der Waals forces is the molecular mass or molecular size. So from Cl to Br to I, the molecular mass or molecular size increase greatly. So that is why they have a higher, the boiling point increase gradually. Okay. So this is for number 6A. Then for 6B, discuss the bond energy of hydrogen fluoride to hydrogen iodide. So in here you can see that the bond energy become less and less positive. That means lesser and lesser energy is required to break the covalent bond between HF. So why is it happen? So now we are discussing about breaking a covalent bond. So for breaking a covalent bond, we must start from the angle of atomic radius and atomic size. From the atomic radius and atomic size, then you can deduce about bond length. Okay. So when you have a greater size, bond length is longer. And finally, you conclude it by bond strength. So longer bond length, easier to break. That is why it requires only lower energy to form. Okay. So the 3 marks definitely stating that bond energy decrease from HF to HI as atomic radius increase. So this will increase the bond strength or bond energy from HF to HI. So this is how we are going to answer for question number 6. Question number 7. All hydrogen halide form strong acid when dissolved in water except for hydrogen fluoride, except this statement. So in here you have to mention that hydrogen fluoride dissolves partially inside water. Why? Because hydrogen fluoride, the hydrogen bond inside hydrogen fluoride is stronger than hydrogen oxide. Furthermore, if you want to form the acidity in here, so general equation in here is HX plus with H2O. Okay, you form H2O plus X minus. Okay, so in here, the way of how the oxygen act as a Lewis base attacking the hydrogen will determine based on the number 1 is definitely the bond length. Because fluorine is a small atom, so their bond length of HS is very, very short, hence very hard to break. Okay. Furthermore, the high electronegativity of fluorine makes the hydrogen bond become stronger. So that is why it dissociates partially inside water. Okay, for the hydrogen fluoride. Okay. Okay. So with that, that is for question number 6. Finally, we go to question number 7. Lithium, beryllium, and fluorines are elements from the period 2 in the periodic table. Lithium and fluorine reacted. It formed white solid in high melting point. However, when beryllium and fluorine are gently heated under mild condition, it form a dimer of Be2F4, while after heating strongly, it becomes a monomer of BeF2. Okay, so A, deduce the type of bonding and draw the Lewis structure of white solid form when lithium is heated with fluorine. So here you have to draw the structure. So Li plus F minus give LiF. Okay. So this is for lithium and fluorine. Okay, then B, draw the structure of the monomer and the dimer for BeF2 and B2F4. So BF2 is among one of the most rare species because usually beryllium is a metal, fluorine is a non-metal. So usually when metal react with non-metal, it will form ionic compound, but not beryllium fluoride. Beryllium fluoride, due to its nature of small size and high charge, so it can easily has high charge density. High charge density will lead it to form a high covalent characteristic. Okay, so that is why even though BF is a metal, non-metal, but it is not ionic compound, it is a covalent compound. So how does the monomer of BF2 looks like? So this is how BF2 looks like. And how does the dimer of B2F4 looks like? So this is how the dimer looks like here. So one of which is 1 mark, so that is for B. And finally for C, explain why compound formed by the reaction between lithium and fluorine has a higher melting point between the compound between beryllium and fluorine. So in here, when you say about melting point, boiling point of a compound, first of all, you look from the angle of ionic, whether it is ionic or covalent. So we already stated that bromine and fluorines are, beryllium and fluorines are covalent compound. This will make lithium fluorine is an ionic compound. Okay, so when inside an ionic compound, you have to first mention that LiF is whole, but LiF have is formed by strong ionic bond, hence have is held by strong electrostatic attraction forces between the oppositely charged ion. Okay, whereas BF2 is a simple covalent molecule. Whenever you are explaining about melting point, boiling point, especially when it comes to covalent compound, try your best to explain like this. It is a simple covalent molecule held by weak van der Waals forces. So that is why it has a low melting point or boiling point. Okay. Okay, so I believe that is all for the objective parts that I want to discuss with you today. So hopefully you all will be able to benefit from it. So I guess that is all for our video today. So see you all next time. Okay, see you all tomorrow. Okay, so that's all. Goodbye.